I also did number 2 as an example from this worksheet, so I'm going to go through that one now. Number 2 is just another kinematics problem. It says a Falcon 9 rocket comes towards the ground at 300 meters per second. When it fires its engine, it accelerates at 3 Gs upwards. How far above the ground should it fire its engine so that it softly touches down on the ground? A G is defined up here, so a G is the same as 10 meters per second squared towards the ground. That's just the acceleration due to gravity. We sometimes call that G in physics. If it's going at 3 Gs upwards, that means 30 meters per second up. All right, I'm going to start off with my picture. So I've got a rocket here. All right, it's falling downwards towards the ground, so its initial velocity here is 300 meters per second. It says comes towards the ground at 300 meters per second. So at the beginning of the problem, it's coming towards the ground at 300 meters per second. When it fires its engines, it's going to accelerate upwards. So it's moving towards the ground, but it's trying to slow itself down. So it's going to, as it's coming down, it's going to start firing stuff out of there and slow itself down so that it stops at the ground. So what we want is, if this is the ground, we want to have the rocket come to rest on the ground. And while it's firing its engines, it's accelerating upwards at 30 meters per second squared. Okay, so it's moving downwards at 300 meters per second. Once it fires its engine, it's going to start accelerating that direction. This is similar to throwing something into the air, where your velocity is the opposite direction of your acceleration. So if you throw something into the air, let's say you throw it at 30 meters a second, then your acceleration for anything just thrown into the air is always 10 meters per second towards the ground. What that means is the object's going to slow down until it stops. And then in the case of something in the air, it's going to start speeding up again. In this case, we've got something where it's moving downwards, but it's accelerating upwards, so it's going to slow down, and we want to have it stop exactly when it hits the ground. Okay, so we're going to say that this position here is x initial. We'll say that this is x final. I'm going to call this the positive direction. So anything that way is positive, anything that way is negative. Now I'm going to write down what I'm looking for. So it says, how far above the ground should it fire its engine so that it softly touches down on the ground? All right. So what I want to find then is x initial, because that's how far above the ground I am when it needs to start firing its engines. All right. So I'll write that down, x initial here, and then I'll write down what I know. So x final, I want it to stop when it's at 0. So I'll call this 0. So x final is equal to 0. I want it to, when it gets to its final position, I want it to be moving at 0 meters per second. So I don't want it to come crashing into the ground. I want it to like gently touch down, so it's going to come to a stop right there. So I'll say v final is equal to 0. The initial velocity is given by the problem, so it's 300 meters per second that way. Because it's pointing down, I'm going to call that negative. So vi equals negative 300. My acceleration is pointing up, and it's 30, so that'd be a is equal to 30. I believe that's all I know. So given that, now I'm going to look through my equations. I want to find some formula that ties this to these things and doesn't include variables that we don't know. I don't see a t, so the first one, second one, and third one wouldn't work because those all involve t, so I'm going to choose the fourth one. Okay, so that I'll start off with vf squared is equal to vi squared plus 2a delta x. All right. At this point, I'm just going to rewrite this formula, substituting in the numbers I know for the variables that are in this column here. So v final, I'll put 0 squared is equal to v initial squared, so that'd be negative 300 squared plus 2, and then a is 30, and then delta x is what we're trying to find. So I'll leave that there. So in this case, I guess I don't have delta x written down, but what I can do is I can say delta x is equal to x final minus x initial. So instead of writing delta x, I could write delta x is equal to 0 minus x initial, because x final is 0. So delta x is the same thing as negative xi. So as I simplify this, I'm going to replace delta x with negative xi, because that is what I'm finding on my paper here. So I'll rewrite this again. So 0 squared is just 0 equals negative 300 squared. That's going to give me 90,000. And then I'm going to say plus 2 times 30 times negative xi. So what I did here is I replaced delta x with negative xi. All right, good. So now I'm trying to get xi all by itself. I've got a 90,000 on this side and a 2 times 30 on this side, so I've got to get rid of both of these. I'll start with the addition. So I'll just subtract 90,000 from both sides, minus 90,000. So I end up with negative 90,000 is equal to 2 times 30 times negative xi. All right, 2 times 30 is just the same as 60, so I can rewrite that as 60 negative xi is the same. So if we say negative 60 xi, that's valid as well. So we get negative 90,000 is equal to 60 xi. Then to get xi by itself, I just divide by negative 60 on both sides. So 90,000 divided by negative 60 gives me positive 1,500. And the units are going to be meters for xi. So that's my final answer. So the rocket needs to fire its engine when it's 1,500 meters above the ground if it wants its final velocity to be 0 when its final position is 0.